Hello everyone. In today's session, I am going to discuss about the Baeyer Villiger oxidation reaction. Now, in Baeyer Villiger oxidation reaction, there is insertion of oxygen adjacent to the carbonyl group of the ketone. Now, in the acyclic ketone on Baeyer Villiger oxidation gives ester as a product, and in case of the cyclic ketone, we get the lactone as the product. So the reagent used for this reaction, or reagent is for this transformation, is as reagents for the Baeyer Villiger oxidation reaction. Now, first reagent is a metachloroperbenzoic acid, then peroxybenzoic acid, then peroxyacetic acid, then trichloroperoxyacetic acid, then hydrogen peroxides. Okay, now etc. Now, these reagents used for the oxidation of the ketone to the ester in case of the Baeyer Villiger oxidation reaction. Now, first see the structure of the MCVA. This is the commercially available reagents used differentially in the Baeyer Villiger oxidation, and the structure C double bond O OH and chlorine at the beta position. This is the structure for the metachloroperbenzoic acid. Now, using the metachloroperbenzoic acid, we see this transformation with mechanism, that is unsymmetrical ketones on Baeyer Villiger oxidation using the metachloroperbenzoic acid. Okay, now let's see the mechanism for this reaction. Okay, now let's take example. Just a minute. Okay, this transformation using the metachloroperoxybenzoic acid, that is MCPA. It gives the product, that is the insertion of oxygen at the more separated sites of the ketone. Now, how can we get this product and not this one? Is that was A or B? We get the product A and not the B. Now, why there is not formation of the B? We see the mechanism for this reaction. Using mechanism, we get the clear idea about the Baeyer Villiger oxidation reaction. Okay, now in first step, lone pair present on the oxygen abstract the proton from metachloroperbenzoic acid, or simply MCPBA. Okay, in first step, abstract the proton, this this is the equilibrium state. Now we get C double bond O OH. There is oxonium ions formations there. Okay, now this oxyanion of the metachlorobenzoic acids attack at the electron deficient carbonyl center. Now, first extracting the proton from the acid gives the it's a very electron deficient center. Okay. Now, second attack takes place at this position, that is the electron deficient carbonyl center. We get the OH here. There is a methyl groups. Now, oxygen. There is another oxygen is there. Okay. This is the chlorine. Now, understand up to that step. Okay. We see step by step. That is in first step abstraction of a proton. Then in second step attack at the carbonyl center. Now, in third step of the mechanism, lone pair goes here and using that on which group migrate over the oxygen, because this oxygen is very electron deficient oxygen. That is, this oxygen withdraw electrons towards its state. So this oxygen is very electron deficient, and because of that, there is formation of the transition state, which is the cationic transition state formation is there. So those group which stabilize the cationic transition state is the electron donating groups and not the electron withdrawing groups. So electron donating, that is the more substituted group, is the more electron donating. Now, so there is a propyl groups and there is a methyl groups. So because of the inductive effect of this 2CH3, this is the more donating groups, or which can stabilize the transition state. Okay, so this group is migrated here. We get oxygen inserted in between inside the more separate sites plus this oxygen. Just 1 second. Okay, and again this extract the proton in workup state. Okay, now we get this is a final product. Now then if okay, in this case there is a methyl group and this is the isopropyl group. Okay, now but when there is again tertiary group, cyclohexyl groups or phenyl groups, methyl groups, then which is the order for these transformations? Okay, which group migrates? There is an order for the migration, or that is the migratory aptitude for the Baeyer Villiger oxidation reaction. Okay, so we see the migratory aptitude for the Baeyer Villiger oxidation reaction, and using that migratory aptitude, we see more example based on this mechanism. The mechanism is similar for the all example, but migratory aptitude has no migratory aptitude okay, migratory aptitude. This is a tertiary alkyl migrates preferentially, then cyclohexyl, okay, then secondary alkyl, okay, this is alkyl, then phenyl groups are in between, that is a there is aromatic compounds. Okay, then primary alkyl, then methyl, and at the last step is hydrogens. Okay, this is the migratory aptitude for the Baeyer Villiger oxidation reaction. Using that migratory aptitude, we see the few example. Okay, on treatment with the metachloroperbenzoic acid. Okay, now let's see this example. In this case, on this side there is a phenyl rings. Okay, and this is the methyl groups. Now see the migratory aptitude. That is a phenyl has the more migratory aptitude as compared to methyl. So insertion of oxygen takes place at these sides and not on the methyl sides. Okay, so we get the product oxygen of insertion. Okay, okay, this is a very simple reaction. We see another example. Now again MCBBA, metachloroperoxybenzoic acid. Now in this example also, this is the secondary carbon. Okay, and this is the primary. So migratory aptitude for the secondary is more than the primary. Using the migratory aptitude we get the product. Okay, okay, then let's see the second type of the example. Now in between the phenyl rings or aryl rings, okay, which is the migratory aptitude. Now for this, see the example. Suppose, okay, at the para position is the methyl groups. This is the first example. Or and again phenyl rings, it's a nitro groups. Same reagent, metachloroprobenzoic acid, metachloroperbenzoic acid. Then which group migrate preferentially in case of the Baeyer Villiger oxidation reaction? Now in this side there is a phenyl groups and this is the para-methoxyaryl. Okay, now the electron donating or which can stabilize the positive charge in the Baeyer Villiger oxidation reaction, that this group is migrated. Okay, those group which stabilize the positive charge transition state which is migrated. Okay, now as compared to phenyl, this stabilize more strongly or provide the stabilization for the transition state. So oxygen insertion at this side and not the phenyl side for this example. So C double bond O, okay. Then in next example, this is the nitro group, that is the electron withdrawing groups. Okay, which withdraw electron towards itself. So it is this, when we migrate these groups in transition state, then it destabilize the transition state. And if we migrate this phenyl group which stabilize the transition state as compared to these groups, so which group, those group which stabilizes transition state, it is migrated. So in this example, there is insertion of oxygen on this side. If nitro is present, now note, there is a note here that more electron releasing group, more electron releasing group, more electron releasing group migrated in Baeyer Villiger oxidation. In Baeyer Villiger oxidation reaction, that is a more electron releasing group migrates in the Baeyer Villiger oxidation reaction. Now, okay, this is all about the which group is migrated. But what about the stereochemistry of the migrating groups? If chiral center is present at the migrating origin, then what about that? In case of the Baeyer Villiger oxidation reaction. Just 1 minute. Okay. Let's see the example. This is the methyl groups. Okay. Okay. On which we added metachloroperoxybenzoic acid. What we did? Okay. There is no problem. There is a this secondary alkyl group is migrated, or cyclohexyl group is migrated. Okay. This is the A group, or this is the D group. B is migrated. There is no problem. But what about the stereochemistry of this migrating origin? What about the stereochemistry of this migrating origin, or what about the stereochemistry at this chiral center? Okay, so there is a retention of the stereochemistry in Baeyer Villiger oxidation reaction, because in the transition state there is a migration from migrating origin to the migrating terminus, that is a 1-2 migration, or in case of the 1-2 migration there is a retention of configuration or retention of the stereochemistry. So there is a no change in the stereochemistry at the migrating origin, okay, after migration. So there is a retention of stereochemistry. Oxygen inserted here. So retention of stereochemistry means retention of stereochemistry means no change at chiral center. Okay, stereochemistry of the chiral center remains same. There is a retention of stereochemistry. Okay, understand this point? Now we move towards the next type of example, that is in case of the bridge bicyclic systems. In case of the bridged bicyclic systems like this, okay, or simply we take the first example like this one. So that will go CS3. Okay, in such cases there is a migration of these groups and not the methyl groups. So On treating with the metachlorobenzoic acid, we get the product. The oxygen insertion is there, C double bond O CH3. Okay. Now let's see the another example based on these types. The OME is there. Okay. Now we get the product. Now let's see this is the primary center and this is the secondary center. So insertion of oxygen on these sides and there is no any interference of this bond. Okay, because of the steric and conformational factors. So insertion of oxygen at this position, there is a retain, there is a OMA groups, this is the hydrogen. So this is product is formed. Now let's see the Baeyer Villiger oxidation reaction of alpha beta unsaturated compounds. What will happen in case of the alpha beta unsaturated compound? Now see this example. Okay, and treating this with metachlorobenzoic acid. Okay, now what about this example? There is a formation of the two products. Which one is there? The insertion at more separate sides along with epoxidize the double bond and also only epoxidation and not the insertion oxygen. This is the epoxidation using the metachlorobenzoic acids. Okay, and this is the Baeyer Villiger oxidation reaction. Now this gives the 80% product, this is the 20% formation. Okay, so what point you get in case of the Baeyer Villiger oxidation reaction? We see the step by step. That is the in first case, that is for the symmetrical ketone we get the esters. For asymmetrical ketone use the migratory aptitude. For the asymmetrical ketone, cyclic ketone use the lactone. Stereochemistry is retained in case of the Baeyer Villiger oxidation reaction. Okay, thank you for the watching video.